we're starting on vectors. So we're already in the first page or two of notes. Everybody, vectors have two values measured by what? Direction, good, and magnitude. Thank you for all the response. All right, so we just indicated that these two vectors here, this vector and this vector, since they have the same length and generally the same direction, are basically the same vector, right? Same value right here. They may not be the exact same vector, but we can say they're equal vectors. Okay. All right. All these are identical vectors, and notice all these have this little arrow over the A right here. You recall back to the very beginning of the year, this is how we indicate or we can differentiate a vector from a scalar. All right, a scalar might just be like a letter. A vector is always going to have an arrow over it. Now, I will say, sometimes we get lazy. Don't always put the vector over top, the vector arrow over top. But generally speaking, from here on out, we're going to be dealing pretty much with vectors and nothing else. Time is really the only thing that's scalar. But you know that. So almost every value from here on out is going to be a velocity, which is a vector, or displacement or acceleration, all of which are vectors right here. Okay? So, this is why it's important to always write units down for a value. All right? You're sitting in the middle of the town square and you say, hey, where's the library? And they're like, 0.5, north of here. 0.5 what? What's one value? Not Maddie. Maddie. Kenzie.
Miles.
Okay, it could be miles. All right. What's another one, Tori?
Yards.
Yards, sure. 0.5 yards. All right, now I'm at the library, right? Good. Okay, so we don't know unless we have a unit right there. So the unit is very important. So we've got a number, this is the magnitude, and the unit tells us what kind of measuring system that we use, because we use a bunch of different measuring systems. But also direction as well. And here's where we want to spend a little bit of time right here. Direction. There's a couple different ways we could measure direction, and I believe it was, we said north, south, east, west a couple minutes ago. Is that Casey? Was it Kenzie? All right. North, south, east, and west. That is one system we could use, and we might just wind up using. All right. Another system, and I'll come back to this in a minute, another system that they use in the military is, I forget what it's called, I think it's called.
I know what it is too.
It's like some long word. I can't remember. Basically, it's a system where north is 0. Okay.
I can't remember.
Or is it east 0?
No, it's north 0.
So this is 90, all right. So west would be 90, 270, and east would be 180, sorry. 180, 270. And 270. All right. So if you're in the military, all right, you don't report back to your commander, hey, I'm going east. No. You say, hey, I'm bearing 270. I'm bearing 270.
Yes. Bearings. They are bearings.
Well, it is called bearing, but I think it has a name too. I can't remember the name. But anyway, the military uses that. I'm bearing 0. People going north. Okay. Or any direction in between. I'm bearing 354. I'm bearing 275. I'm bearing whatever. That's fine, and the military does use that. But I think we're going to use a system. We're going to decide to use a system that I think is a little bit easier. All right. The problem with this is that it's a full 360 degrees all the way around. All right. And if I say, quick, what direction, Brianna, are you going if you're bearing 172? You're like, somewhere in here. Okay. But if we use this first system that I'm going to spend more time on, it might make a little more sense. Okay. What we're going to do, I think, is measure every angle from the horizontal. All right, darken this in right here, or highlight that, or do whatever. We're going to measure every angle from east, north of east, or south of east, or north of west, or south of west. The reason this is convenient for us is because we're used to thinking about, well, like in math class, when you first measured angles, you probably measured an angle from the horizontal, right? What angle is that right there? I don't know. Let's keep it in nice, convenient little quadrants. All right? 4 quadrants, all based from the horizontal. So here's what we're going to do. We're going to have 4 angles right here. Actually, well, we've got 4 angles right here with these blue lines. Generally, what angle would you say that is between the vertical and horizontal? What do you think, Maddie? 0, 90? Yeah, 45. Okay. So we're going to say this first angle right here, and I'm going to do these in different colors too. We're going to say that's 45 degrees. Okay, direction of it. North of east. North of east. So you go east and then 45 degrees north. Make sense so far? Let's say these are all 45, which it looks like they are. Okay. Then if that's the case, what would we call that angle right there? Nick, would you weigh in right here? We're going to say they're all 45, right?
Right.
So this would be, I'm sorry, we're measuring from the nearest horizontal, right? So 45 what of what? Right here. This is 45 degrees. If this is north of east, then this is
South of east.
You got it. 45 degrees south of east. South of east. East is horizontal, and then either north or south. The nice thing about this is you can't have an angle more than 90 degrees north of east. What if you do? Now all of a sudden over here it's north of something else. What's that angle as based from the horizontal? That is right there. Casey, help me out here. What angle is that? 45 degrees, what?
North of west.
Nice. 45. North of west. And Mackenzie, what do we call that?
45 south of west.
Nice. 45 degrees south of west. All right, these are all going to be based from the horizontal right here. And it's going to be important that we kind of stay true to that, because it might be easier to say, okay, if you've got a really steep angle like right here, you might think, oh, I'd rather just deal with 1 or 2 degrees. So that's 1 or 2 degrees east of north. Well, that's kind of sort of mess your system up a little bit. All right, we're going to measure all of our angles based from the horizontal. North of east, south of east, north of west, and south of west. Okay? If anybody's in the military or ROTC and prefers the system, sorry, I'm not doing that, but I'm going to measure them all north of east, south of east, north of west, south of west. All right, a couple different things about vectors that are should be familiar. All right, you can add them or subtract them pretty much in any order. All right, vector A plus vector C is vector, plus vector B is vector C. All right. So, what does vector A plus vector B look like? Now, this is vector A right here. Okay, that's a little arrow over top of vector A. And let's just say they're displacement vectors. All right. This would be, how many degrees north of east would that be? 0, right? 0 degrees north of east. This is just a little example. I'm making up off the top of my head. Okay, and it's going to have some value, right? Let's say it's like displacement, where it's 5 meters at 0 degrees north of east. Okay, what happens when we add another vector to it? Well, we say, okay, once you get to this point, now we're going to follow vector B, which is, say this is 45 degrees north of east right there. Maybe the same length, so 5 meters at 45 degrees north of east. You just add the tip of the one vector to the tail of the other. You just add them together like that. So say you're on a treasure map right here, or you're on a treasure hunt. Here you are, map in hand. Okay, and the map says, go 5 meters, 0 degrees north of east. You're like, great, I'm here. And then the next vector you're given is, all right, now go 5 meters at 45 degrees north of east. Great. But how could these two vectors be summed up in one vector? What do you think, Matt? How could we make that, how could the writer of the map have made that easier for the reader? You like taking roundabout paths?
45 degrees north.
Well, it wouldn't be exactly 45, but it would be, this angle is less than that angle, right? But it's some other angle north of east, right? So we could say, hey, this vector right here, vector C, is equal to the sum. It does the same thing as the sum of vector A and vector B. All right, so that's what that means right there. If we were to change the signs, if we were to subtract vector B, if we were to go here and then turn this vector around and go down here somewhere, you get a completely different resultant right here. So vector D is a resultant of A minus B. So if we subtract things or add them in different orders, we get different results. Or not different orders, but with different signs. The order actually doesn't matter. So B plus A. All right, what if we took this guy right here and went up first? All right, did B first and then A. Would we get the same spot? You got it, absolutely. So the commutative property, order, it doesn't really matter. But not changing signs, yeah, absolutely, because well, vectors depend upon signs. Okay? All right. Let's see. Yeah, I mean, this is familiar to us. If you have any two values, and A minus B equals C, B minus A equals negative C. All right, these are just like adding positive or negative values. What we want to get into right here is what happens if we multiply a vector though by a scalar. All right. By a scalar. So what is a value that we've been talking about that has a vector and a scalar quantity in the units that we've been talking about so far? What is that?
Speed.
Yeah, well, not speed, but what's the vector version of that?
Velocity.
Yeah, you guys know that velocity, the vector, equals meters, which is displacement, right, per second. Now, it's not multiplied, but it's divided, but it's the same type thing right here. We have a vector made up of a vector and a scalar. All right, well, so if you multiply a vector by a scalar, you'll still get a vector. But depending on what the scalar is, that'll change your original vector right here. Okay? So let's say we have a vector, we've got a velocity vector right there. Okay? What if we multiply that by a scalar that is greater than 1? All right? So multiply this value right here, I don't know, we'll say 5 meters. I would say 5 meters per second. All right? What if we multiply that by something greater than 1? What's going to happen to the magnitude of that vector right there?
Increase.
Got it. All right. Oh, I'm sorry. I did the wrong one first. So that's going to increase. Okay. Magnitude will increase. Good. The direction will stay the same. Because if you multiply this by some sort of a scalar quantity, like seconds or some unit of time, does time have direction? No. So it's not going to change the direction. All right. So that's going to be the same. What's going to happen to the actual arrow that represents the vector? And by the way, these two are going to be sort of intrinsically tied to each other. If the magnitude increases, what happens to the arrow, Rachel? You got it. Longer. Okay. Longer arrow. So we have a vector, we'll multiply it by something greater than 1. Great. What if we have a vector, we'll multiply it by just 1? Well, that's pretty easy. It's going to be the same direction. All right. It's going to have the same magnitude and the same length. What if we multiply a vector by a scalar that is between 0 and 1? That is, we'll say 0.5. Okay? We'll say that's like 0.5 right there. What's going to happen to the direction? Is the direction going to change? Nope, because this is still a positive direction, or this is still basically positive right here. So it's not going to change the direction of it, so it's going to be the same. All right. What if we multiply anything by 0.5? What does that do to the magnitude, Victoria?
Makes it less.
Yeah, less. You know what? I should stay kind of consistent. Increase, decrease, right? Okay, so the arrow then would be shorter. All right, multiplying anything by 0, 0 direction, 0 magnitude, 0 vector. All right. Oops, I can't do that. Basically, it's like I was going to try to illustrate moving 2 meters in 0 seconds, but that would be dividing by 0. If you multiply anything by 0, it becomes 0. All right. So if there's no time elapsed, then there's no velocity. All right. What this means right here is it's somewhere between 0 and -1. So it's negative. Think of it as negative 0.5. Negative 0.5. What does that do to the direction now of the arrow of your original vector right here? Maddie, help me out. What if we multiply this by negative 0.5? You got it. Opposite. Okay, opposite direction, so it's going to be going the other way. Okay. The magnitude. And of course, time can't be negative, but other scalars can be. What if you multiply anything by 0.5? It's going to be short, all right? So decrease. And it's going to be going the opposite direction. It's going to be a shorter arrow, decreased magnitude, therefore the arrow is going to be shorter. Okay. Multiply anything by -1. Well, you're going to have the same magnitude and therefore the same length. But if you multiply any vector by a scalar that is -1, it's going to be the opposite direction. Time can't be negative, but other scalars can. And anything greater than -1, well, again, if there's a negative in front of it, it's going to be the opposite direction. Okay, opposite direction. The magnitude, well, it's going to increase, right, because you're multiplying something by greater than the absolute value of 1, so it's going to increase. Right here, okay. And the arrow, of course, is going to get longer. But just in the opposite direction, you might say, as the original vector. Okay? Any questions on that? There'll probably be some questions about that in your homework. All right, so let's do a couple examples right here. So, we have a vector. We've got vector A, 4.0 meters per second. All right, this is the velocity right here. And you say that that's a vector, and that means that must be a vector or displacement right there. Okay, so it's going at 30 degrees north of west. Do I have, okay. You know, there's actually a different way we could do in the direction as well, but north of west I think is probably, north, south, east, and west is probably the best we'll stay with right here. All right, let's multiply these together. All right, 4 meters per second. At, and get used to doing this little, not ampersand, what is it? For an at sign, I guess. All right. Oops. At 30 degrees north of west. Okay, now, before we go any further right here, let's just sketch that out and see what it looks like. All right, that's our coordinate system right there. What does 30 degrees north of west look like? It's going to be north. It's going to be west. So north of west on 30 degrees, not quite 45, so I'm going to guess it's kind of like that. All right. Sketch it out, visualize it. Okay, times 2.0. So basically, we're just taking this vector and we're multiplying it times 2. So our resultant vector right here is going to be quite small. All right. So what's the value of that going to be? Who do I hear from? Brianna. What's the magnitude? The resultant magnitude. Same direction. Direction hasn't changed. Oops, my period went away here. Dot, there you go. 4.0 times 2.0. Thank you very much. 8.0 meters per second. Let's not stop there. At what? Nick?
30 north of west.
30 degrees north of west. This next example right here is a secondary coordinate system that we could use, but we'll stay with north and west and just kind of translate it. All right, so let's multiply this vector by this scalar right here. Okay, so in fact, let's turn this. Well, you know, I'll do it both ways. Right. We have our original vector right here. I'll use different colors. All right, so that's A right here. We've got a vector with a magnitude of 18 meters, so it's probably a displacement vector, right? It's just a length. At 50 degrees above the negative x-axis. 50 degrees above the negative x-axis. Where would that be? Which quadrant would that be right here? 1, 2, 3, or 4? Which quadrant would that be in? What do you think, Mackenzie? What's that?
1.
You got it right here, right? So 50 degrees, here's the negative x-axis, and 50 degrees above is a little more than 45 degrees, right? I'm going to try to stick, for the most part, with north of west, south of west, north of east, south of east. But sometimes, just so you get used to this, you might come up against this. So 50 degrees above the negative x-axis is the same thing as saying what, Zach? And then I'll answer your question.
50 degrees north of west.
You got the same thing as saying 50 degrees north of west. In fact, I think that's easier to write out because it's, you know, above the positive and negative x-axis or whatever. The negative x-axis and above it is the same thing as saying north of west. What are you going to say?
You said that was quadrant 1 that was in.
Oh, I just picked them random. I said 1,
Right.
2, 3, 4. She said 1.
All right, just note the quadrant system a different way. That's all.
No, you're probably right. I just arbitrarily picked.
Yeah.
Yeah, I'm sorry. I just said which of these. Yeah, this is probably 1, right? Because it's a positive, positive,
Mm-hmm.
positive, negative, 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 positive. Yeah. I just kind of pointed right here. All right. So let's multiply them together. So is the multiply a vector by a scalar going to change the direction? No. What's going to happen right here? So 18, so magnitude 18 times negative 0.5. It's going to be interesting. So two things are going to happen to this. Let's make this result to be, make the result be black. All right? Or make it red. Okay? Vector B is red right here. If we multiply it by a scalar, which is negative 0.5, first what's going to happen to the magnitude? It'll be halved, right? And the negative does what to the direction, Nick?
They said opposite.
Good, opposite direction. So let's try to cut that in half right there. Is that about half? And it's going to be the absolute opposite direction, which is interesting. So the question now is, what's the direction now of our new vector? All right, so what is half of 18? So that's 9 meters. You're like, oh, wait a minute, it should be negative 9? No, it's just 9 meters. We're going to incorporate the negative part into it when we talk about the direction. Okay? So, which angle should we measure here to talk about the direction of this resultant vector right here? This angle or this angle? Matt, what do you think? Top one or the bottom one?
Top one.
Top one, right. You have a 50-50 chance, right. Okay, we measure always from the horizontal. And so what is true about this angle and that angle right there? Yeah, there are what's the word? Not, Zach, you probably know. Not complementary, not supplementary, not opposite interior. Opposite angles?
You're just the same.
Yeah, they're just the same. All right. So it's the same value or same angle at 50 degrees But now what are we going to tack onto the end of it that talks about its direction?
Due south of east, or
South of east, right? South of east, or we could say below the positive x-axis. That's the same way of doing it. All right. This is going to be our resultant vector when we add, or when we multiply this vector times whatever scalar we have. Okay. All right. Let's do this last one right here. I'm going to sketch this down. Here, we'll make this guy green. All right. So our original vector is going to be 6 meters at due west. Well, that's easy. All right. That right there is due west. Nowhere above or below the x-axis, just kind of right on the axis right there. All right. We're multiplying it by -1.0. Does multiplying it by a factor of 1 change anything? Richard Grady, what does it do to the magnitude of it? Stays the same, right? But the negative tells us opposite direction. Okay, so let's draw it first. So I'm going to make resultant 1 blue. All right, so vector B is going to be blue, and so that's going to be same magnitude, opposite direction. So our resultant vector is going to be 6 meters. Don't forget the direction. At what? How would you say that, Victoria? Make a little better arrow here. Due east. Yeah. At east. You could say 0 degrees north of east. That's fine too. All right. But all those are ways of notating direction around a coordinate system. Any questions on this, you guys? Got it so far? We'll be adding vectors a little bit later, and you're going to be using your rulers. And did I give you guys protractors? Oh, fine. Well, we got a bunch of them right here. You have your own rulers, but we're going to have protractors as well. So you can start adding vectors like we did before, tip to tail, which means it doesn't matter in which order you do them or add them together. All right, I'm going to stop here for now. All right, we're going to actually wind up breaking vectors into, well, let me just give you like a little preview of tomorrow. All right, into 2 parts. So let's say we have a vector right here. This is going to be kind of tomorrow. We're going to have, give me a magnitude. Brianna. So was it 60 or 6? 60 or 16? 60. 60, thank you. Somebody give me a direction that this could be.
30 north of east.
North of east and 30, I love it, okay? 30 degrees, oops, sorry, that's right there. North of east, all right? So we'll probably write that out at 30 north of east, okay? Good. Tomorrow, we're going to be getting into taking this one vector right here and break it into 2 parts that lie on 2 separate axes. So this is the x component of that vector. And we haven't used red right here. And that's the y component of that vector right there. And we're going to see how a given direction, or given magnitude and a given direction, and taking 2 other separate components and putting them at right angles to each other, is going to, number one, first of all, incorporate trig, and secondly, help us to add all kinds of crazy different angled vectors together. As long as you just are careful to pay attention to details. All right? So, we have like 6 minutes left, something like that. I want you guys to start on numbers 1 to 6, which are going to be due Wednesday. And what happened here? Yeah. Anybody else have trouble with the trig? Right here. This right here is basically the foundation for that right there. So we'll clear that up, okay?
I just don't know if I did it right or not. Like I just kind of
Okay. That's fine.
use the functions and
You want me to take a look at it now?
yeah.
Sure, absolutely.
I got a lot of decimals and I was a little scared about that.
Don't be scared of decimals.
Yeah.
I mean, sometimes you should be scared of decimals, but
I do
especially
have-
if you have an inherent fear of decimals. But no, I'll take a look at it right now. The rest of you guys start 1 to 6, okay?
I do have one just like quick question.
Yes,
of
sir.
How to show work with these, because most of them I just figure them out either here, just calculate
Well, what I would do is I would write down
this in the Pythagorean form, because that's how I found these. I mean, I know you can use trig functions, but I usually did Pythagorean.
You can, but start getting used to using trig functions.
Alright.
So what I would do is, so what are you, you're solving for?
Like if you're solving for a side, you can use a trig function or a Pythagorean.
So this is like 30 or this?
It says 60, but
Yeah, it
yeah.
doesn't look like 60, yeah. All right, of course that's going to be a right angle right there. So if you're solving for, this is angle A and you're solving for side A.
You
And
want
what do we say, the hypotenuse for 22?
22, yeah. You can do sine 30 equals a over 22, or 22 squared. Well, we don't have the sides yet, so you have to use one. But if you find another side,
Well, you need this side.
and then you need one more side, and then
Right, so what I oftentimes do, just to remember just the order, or the
SOHCAHTOA.
SOHCAHTOA, right, so I would say sine of A equals
A over C.
A over, yeah, 20, or, well, yeah,
C.
hypotenuse. All right, then I would just rearrange it and then solve it.
All right.
That's one way that you can actually show your work. All right.
okay.
Or, I know you can think through stuff.
Well, I usually used a squared plus b squared equals c squared as well for sides, because this is,
But when you solve for an angle, though,
Yeah,
say
you need to
say
do-
you have this side and this side, you know this angle.
you do inverse trig.
Exactly right, which is why you're gonna want to get used to doing those, or at least writing down the sine function. Okay?
Yeah, okay.
I'm sorry, Victoria. I was just going.